Hi everyone, in our last video we have looked at Newton's third law. Now let's move on to look at our section 2, which is called normal reaction force. So if you have a look at an object on your desk, maybe it's a book, maybe it's a phone or a water bottle. So have a look at this object on your desk. You know there's a weight acting on it and pulling the object downwards. But why it is not accelerating downwards? There must be an upward force to make the net force 0. Otherwise, as we just said, the object will fall through the table. Now, this force exerted by the table on the book is called the normal reaction force. So, whenever an object is in contact with a surface, the surface exerts a normal reaction force on it. This force acts in a direction perpendicular to the surface and away from it. So can you please make note. So you can highlight this. Okay, so this is the important bit. The force acts in the direction has to be perpendicular to the surface and it's always away from it. Right, let's look at some diagram. So here in the first diagram, we have a man pushing onto the wall. That means the wall will have a normal reaction force. So you can see the force here is perpendicular to the wall, and we normally use capital R to represent normal reaction force. Sometimes in other textbooks you may see capital N, but they mean the same thing. Okay, so here the normal reaction force acting on the wall goes perpendicular and away from the wall. If you look at this box resting on the table, the weight is pulling the box down, and now we have a normal reaction force goes perpendicular to the surface of the table and away from it. And here we have a box resting on a slope, and the weight, remember the weight always pointed vertically downwards, but the normal reaction force always goes perpendicular to the surface. So this time it perpendicularly goes upwards and away from the surface. And in the last diagram, we have a slightly strange surface, which is a circle. So imagine you have a box resting on top of a bowl. Again, the weight goes directly downwards. However, the normal reaction force R goes perpendicular to the surface. Right. Let's look at an example. So, in this question, it says a person of mass 76 kg is standing in the lift. Find the magnitude and of the normal reaction force exerted by the floor of the lift on the person when the lift is moving upwards with acceleration 2.2 meters per second square. Okay, so right, firstly, now in the question it says the lift is actually moving upwards. So this is our positive direction, and the acceleration is 2.6 meters per second squared. Okay, well, if it's moving upwards, that means the resultant force must be going upwards as well. So let's use F equals to ma and write down what is our resultant force. So imagine this is the person, and those two will be the force acting on the person. The weight, mg, will be acting directly downwards, and the normal reaction force acting perpendicular to the surface, which is the floor of the lift, and directly point upwards. So, as we said, the lift is going upwards, so the overall force, the resultant force, must be pointing upwards. So that means we will have the normal reaction force R plus Now, because the weight is acting downwards, which is opposite to our direction, so that has to be negative mg. And that equals to ma. Or we can put those two signs together and just say that r take away mg must equal to ma. Okay, so let's substitute the number in. So r minus m, the person's weight, the mass is 76. And we normally use 1.8 for g. So that equals to 76 times by the acceleration, which is 2.6. Okay, so r now equals to 76 times by 2.6, and then move this across with plus 76 times by 9.8. And put in the calculator, you will get the normal reaction force R equals to 942 Newton. So this is a normal reaction force you would get when the lift is moving upwards with an acceleration. Well, however, what about if the lift is moving downwards? Would you have the same normal reaction force? Well, let's look at the next part. Okay, so the same person standing in the same lift. Now we're going to work out the normal reaction force when the lift is actually moving downwards with an acceleration of 2.6. So let's draw our direction. So this time going downwards is our positive direction and acceleration is still 2.6. Now this time when we use our F equals ma, be careful. Now, because the lift is moving downwards, that means your resultant force will be positive towards the, when going downward, will be positive. So this time we would have to use mg plus, now, so that's positive, this is going down, but now normal reaction is going upward, which is against our positive direction. So have plus a negative r, and that equals to ma. So can you see the difference to this equation we're using compared with part A now? Okay, so let's substitute the number in. So m is 76 times by 9.8 minus r equals to 76 times by 2.6. So this time r will equals to 76 times by 9.8 minus 76 times by 2.6. And r come out to be 547 Newton. Okay, so you can see there is a difference to the normal reaction force when the lift is moving upwards or downwards. Right. Let's look at the last part of this question. Now, here it says, what if now the lift is moving downwards with a deceleration of 2.6 meters per second squared? Right. Again, let's draw on the diagram. So it's moving downwards. Okay, so let's still say going down is our positive direction, but be careful what is your A. If it says it's a deceleration of 2.6, then we have to give a negative sign. So A is negative 2.6 meters per second squared. So just like in part B, we're going to put into our F equals ma, and F is mg plus a negative r equals to ma. So mg minus r equals to ma. Substitute the number in, we have 76 times by 9.8 minus r equals to 76 times by negative 2.6. So be careful here. And this time we've got r equals to 942 Newton. And to be fair, you might not need to do this step here. Some of you may have realized that when we have a downwards movement with deceleration of 2.6, It's basically just like the same situation as part A, when you're moving up with acceleration of 2.6. Okay, right. Let's look at something else. Okay, so notice that the normal reaction force is larger when the lift is accelerating downwards, accelerating upwards or decelerating downwards than when it is accelerating downwards. Think about what you would feel if you were actually standing in a lift. If it is accelerating upwards, it feels as if the floor is pushing against your feet. But if it's accelerating downwards, you feel as if the floor is moving away from you. And this is because the normal reaction force in the two cases is different, just like how we would work out in the last example. Now be careful not to confuse normal reaction force with Newton's third law. A common misconception is that normal reaction is the reaction to the object's weight. However, the weight and the normal reaction are both acting on the object itself, so they are not a Newton's third law pair. Because in Newton's third law, you must have the force acting on two different objects. In the example of a book on the table, the reaction to the book's weight is the force with which the book acts on the earth. The reaction to the normal reaction force is the downward force with which the book pushes the table. Okay, so let's have a look at an example. Right, so here in this question, a book of mass 260 grams rests on the horizontal table of mass 65 kilogram. The table has 4 legs and the thrust in each leg is the same. Assume that the table's legs are light. Part A, draw 2 separate diagrams showing the force acting on the book and the tabletop. So I have actually done the diagrams here for you, so let's have a look. Right, so this is the forces acting on the book. So we have the weight acting downwards. So weight equals m times by g, and m, the mass, is 260 grams, which will be the same as 0.26 kilogram. Now remember, when we're talking about the weight, the mass should always have a unit in kilogram. So you have to do some conversion here. Okay, so this is the weight. And that means there will be a normal reaction force acting upwards. Right, let's look at what is happening on the table. So this is the diagram showing all the forces acting on the tabletop. So the table will have a weight, which is 65 times by g. And now here, the book will also try to push down with normal reaction force. And because the table is resting on a floor, so there will be a thrust going upwards in each leg. Hence, there are 4 teeth going upwards, pushing the table upwards. Okay. So, sorry, we haven't done part B. Now, part B, find the thrust in each leg. Okay, so let's have a look at this diagram. So, using this diagram, firstly, we can work out what is our normal reaction force, can we? Let's do that first. Now, because if you think the book is resting on the table, so there's no acceleration, which means the resultant force should be 0. Okay. That means the normal reaction force must equals to the weight. So we can say that R equals 0.26 G. Okay, so that means Well, as we said, the normal reaction force will be the same. So that means this R will also be 0.26 G. So we'll use that later on. Now, let's think about the forces acting on the table. Again, because there's nothing moving, there's no acceleration, so the resultant force acting on the table should be equal to 0. So what we have is all the forces acting upwards should balance with all the forces acting downwards. So here we have T plus T plus T plus T, so the 4 lots of T must equal to all the forces acting downwards. So in this case, we have R and 65G. Okay, so we can now replace R with 0.26G and then plus 65G. So you can now put in a calculator and use G as 9.8. You should get T equals to 160 Newton. So this is the thrust force in each leg. Right, part C. State the magnitude and direction of the force exerted on the ground by the tabletop. Well, so the forces on the ground from the tabletop, well, if you look, the table touches ground with the 4 legs. So that means the ground will experience the force from the 4 legs. So that will just be 4 lots of T. So this is part B, and then part C, the force will just be 40, and that would be 4 times by 160. So that would be 640 Newton. So this will be the force experienced by the ground, and that will be directly downwards. Okay. Let's move on. Right, let's have a look at this example. So, a book of mass 260 gram rests on a horizontal table of mass 65 kilogram. The table is being lifted by a cable attached to it and accelerates upward, as you can see in the first diagram. The tension in the cable is 710 Newton. Find the normal reaction force between the book and the table. Okay, so this is where the normal reaction force will be, and this is the direction. And the whole thing is being put upwards, hence the acceleration is going upwards. Right, so let's look at the second diagram. So the first diagram tells you all the forces acting on the book. The second diagram tells you all the forces acting on the table. So what are the forces acting on the table? Firstly, we have the weight, which is 65G. And secondly, we would have the normal reaction force from the book. Now it will be going downwards. And also because it's being pulled upward, so there will be a tension going upwards. Okay, so let's use Newton's second law and write down all the resultant force for each object. So what do we have? Now, one thing you have to know is if it's going upwards with acceleration A, that means the book and table are both going upwards with the same acceleration A. Okay, so why do we write down, maybe right over here. So what is going on for the book? Okay, so again, we're going to use F equals ma. And let's use going upwards as the positive direction. So that means we would have R plus a negative 0.26G. Now, plus negative is the same thing as just take away. So let's just take away 0.26G. and that equals to MA, and that would be 0.26 times by A. Okay, now let's think about all the forces acting on the table. Again, we're going to use F equals MA, and going up is our positive direction. So what are the forces acting upwards? Well, in this case, we would have the tension, and in the question it says tension is actually 710. So let's use that straight away. So we would have 710 Newton, and those two forces acting downwards, so be negative. So we take away R, take away 65G, and that equals to MA, and M is 65, so be 65A. Okay. So now, can you see in these two equations, G we know that's 9.8, and the only two unknown will be R and A. R and A. So we can solve this simultaneous equation. Well, why don't we make R the subject in this equation? So R equals to 0.26A plus 0.26G, and then substitute this into the second equation. So replace R with a new expression. So let's do that. So now we have 710 minus bracket 0.26A plus 0.26G close bracket minus 65G equals to 65A. So this is from the second equation here. And that should be a 0. Right, so we have now got expand the bracket 710 minus 0.26A minus 0.26G minus 65G equals to 65A. Now A is the only unknown, so why don't we put this all together to the right hand side? So we have 710 minus 0.26G minus 65G equals to, so that would be 65A plus 0.26A. So 710 minus 0.26G minus 65G equals to 65.26A. And on the left hand side, replace G with 9.8, and you can put into a calculator and find out the value, and then divide it by 65.26, and then you will get your acceleration A equals to 1.08 meters per second squared. Now when you know your acceleration, we can substitute it back into this equation to work out the normal reaction force. So when A equals to 1.08, normal reaction R will equal to 0.26 times by 1.08 and plus 0.26G. So the final answer for our normal reaction force come out to be 2.83 Newton. So this question is much harder because you have to consider the force on two different objects, and you have two unknowns, and you have to solve a simultaneous equations. Right. Okay, so let's move on. Now, when two objects are in contact and moving with the same direction, you can consider them as a single particle. Newton's second law, F equals ma, applies with m being the combined mass of the two objects and F being the resultant of all the external force. So let's have a look at an example where we can combine things together. In this question, A person of 72 kilograms stands in a lift of mass 540 kilograms. The lift is supported by a cable that can be modeled as light and inaccessible. Part A. Draw two diagrams showing all the forces acting on the person and the lift. And I have already done that for you, so let's have a look at the two diagrams. So the first one, this is a diagram with all the forces acting on the person. And we have the weight, 72 grams acting downwards. Sorry, I didn't say, shouldn't be 72 grams. It's the weight is 72 G. And there will be a normal reaction force pointing upwards. And that's it. They are the only two forces acting on the man. In the second diagram, this is all the force acting on the lift. So we would have the weight 540 G acting downwards, and also the normal reaction force from the man acting downwards. And the cable is pulling the lift, so there will be a tension pulling upwards. Now remember, both of them will have the same acceleration, and they're both acting downwards. Okay, so let's see if we can work out part B. Part B, let's find the tension in the cable when we've been given that the lift is moving downwards and is decelerating at 2.1. So now, firstly, decelerating at 2.1, what does that mean? That means our A is negative 2.1. Okay, so, well, instead of consider things separately, why don't we combine the person and the lift together and think about what's happening all together? So, part B. If you think we have everything together on this object, what's the total weight? Well, the total weight would be the weight for the man and the total weight for the person, the lift. Sorry, the man and the lift. So the total weight would be 72 G plus 540 G, and the total weight for the combined object would be 612 G. And there is tension moving upwards. So in this case, we don't need to consider the normal reaction force, because if we're putting them together, you can see the R and R will just cancel out. So this is quite useful here. So that means we can now use F equals ma straight away. Okay, and the force, well, as we used going downwards as the positive direction. So let's use the total weight, 612 G, as a positive one. That means the tension would be negative, so take away P, equals to, now what is the M? So the M would be the total mass between the person and the lift. So M would equals to M for the man and M for the lift added together. So M is also 612 kilogram. So that would be 612 times by A, and A is negative 2.1. So you can point a calculator, rearrange it, and remember G is 9.8. So T would come out to be 7,280 Newton. Okay, right. Now let's look at part C. It's a different color this time. That's right. Find the magnitude of the normal reaction force exerted on the person by the floor of the lift. Right, so now what can we do? Right, so let's consider this first diagram here. Okay, so we're looking for R. Now, do we know A? Yes, we know A. And then we say A is negative 2.1. Then we know this. Okay, So actually, we don't need to use tension. We can work it out straight away using F equals ma. So part C, F equals ma. So the F would equals to the weight 72g at negative r, so we taking away r, equals to m, which is 72, times by a, which is negative 2.1. So that would means that your r would equals to 72g minus 72 times by minus 2.1. So r will come out to be 857 Newton. You can put this into a calculator. You should be able to do the rearrangement by yourself. All right. Okay, so I think this part for normal reaction can be a little bit tricky, but again, remember, always draw the diagram and then label the forces separately. Okay, sometimes it's easier to split them into two objects and think about the force separately. However, sometimes it may be easier to combine them together as a one thing and thinking about the normal the tension and accelerations. Okay, so it really depending on the question you get. Now, why don't we do some exercise now? Here are the question 1 for exercise 22B. Question 2. Questions 3, 4, 5, 6, and 7. Question 8, 9, 10, and 11. And here are the answers. So I would strongly suggest you to do question 1 and 2 carefully, draw the diagrams and label all the forces. You need to be able to do that first before you move on to look at some worded questions. And when you're doing the worded questions, always draw the diagram first and label all the forces and which direction you would take as the positive direction.